So I wanted to explain these complex exponential characters in a little bit more detail. I covered this in my video on the C6H point group character tables, but here I'll cover it in a little bit more detail. So these cyclic groups, the C and the S groups or subgroups, if they are just part of a group, possess the property that they will equal 1 when k equals some integer multiple of n. And so, that makes sense if you make a sort of full rotation around your principal axis, then you get back to where you were, and that is the identity element. And that's why we can actually associate them with the complex exponential function, which also has the property that if we have e to the I k pi, or e to the I k2 pi over n, if k equals some integer multiple of n, then this will become equal to 1. And so you may have, seen people talk about like that Euler identity where it's e to the power of I pi equals -1, or maybe you've seen it as e to the power of I pi and then -1 equals 0. Well, if we didn't have this 2 here, then it would be a -1. But a -1 is a half rotation around the unit circle, and so that goes to -1. But if we put a 2 there, it becomes a full circle, and we get back to 1. So that means that k equals 0, 1, 2, all the way to n minus 1 will be sort of members of these cyclic subgroups here. And so often in the literature, this substitution is made where they'll have it equal to epsilon or equal to omega. So my inorganic chemistry textbook uses the epsilon. The sort of older book that I'm using as a guide for this video series uses the omega. And so, that's something you might see depending on which source you are using. And so the version of n being used, whether it's the 2, 3, 4, 5, or 6, will be used. Being used will be defined beneath the table. So you'll often see them put this underneath the table so that like which version of n you are actually using in that table. And so if we look at the C3 group, we get the following 2x2 matrix representations. So we get the identity here, we get the C3 and the C3 squared. And so we can put our omega equal to this e to the power of I pi over 3. So we have n equals 3 here. And so in this first case, the C3, k would be equal to 1. And then in this one, k would be equal to 2. And so that's why you get these omega and its complex conjugate flipped like this. So the representations appear in conjugate pairs, as we see the omega and omega star. We know that from an earlier video that a change of basis with a unitary matrix can give us the real form of these matrices. And so we have our unitary matrix like this, and we could use that. We could conjugate with that on each of these, and we would get these real valued matrices here. So that is something you can do. I mean, that's kind of how you can convert between the imaginary and the real versions. And so here are a few tables here. So we have the C3 table here, and we can think of these ones here as being complex exponentials where k is equal to 0 here. And so this would actually equal 1. I guess you could also have k equal to 3 here, or multiples of 3, and you would get 1. But then the C3 is e to the I 2 pi over 3, and then this which would be kind of like C3 squared is like this. And so we see that this forms a triangle here in the imaginary number field here. And so this 1 here is our E column right here. This one up here would be our C3 column. Then this one down here would be our C3 bar column. And so we can actually see that, if you can see that, that's actually e to the power of 4 pi over 3 times I. And so we see that this actually forms a triangle, which itself has C3 rotational symmetry about the axis right here. And so we see that the complex sort of representation of C3 gives us something that's C3 in the imaginary plane. And we can do the same thing for C4. And so we now see that we have this, which has these 4 points here, and we see that this has C4 symmetry, or rotational symmetry, because we can start right here. We can go 1, 2, 3, and then at 4 we get back to the beginning here. And so we can make our table that looks like this. And so we see in this E we have 1, 1, and the C2 we have minus 1, 1, because if we did a 180 degree, we'd start here and we'd go all the way here to minus 1. The C4 has I, which is up here, so that would just be going from here to here. It has this complex conjugate minus I, so the C4, which this could be looked at as C4 cubed, which would just be going from here down to here down to here, we see is minus I, and so that actually brings us to the negative I here in the complex plane. And so we can do the same thing again for the C5 here, and so we see that this has 5 points on it, and this is a pentagon, and it has C5 rotational symmetry. So you can go 1, 2, 3, 4, and then 5 gets you back to the origin. And we can do the same thing with C6, and you could keep going to different different roots of unity. And so you see that it says 6 roots of unity. And so that has to do with the way, with essentially that what we're saying is that when we do something to the 6th power, so some number to the 6th power, then we get back to 1. So that's why it's sort of the 6th root of unity. So in complex analysis, and when you're thinking about complex numbers, or I guess even when you're doing just like polynomials and allowing for complex answers, then you actually, so you're kind of saying that, if we have something that's I to the 6th power, that equals 1. So something that looks like this would mean that this I is the 6th root of unity. And I think it's actually usually shown with an n like that, and so n to the 6 equals 1 is the 6th root of unity, because it takes 6 times to get around this. But anyway, that is what I wanted to say. I hope maybe this helps give you an even better understanding of what these sort of complex exponentials are doing in our character tables, and so how you can actually relate these complex exponentials to our different cyclic subgroups. And so you will only see the complex exponentials in subgroups that have C or S. So I showed it here because technically you can think of the other ones as having those complex numbers, but it would just be something that would look like, like 1 plus I times 0. And so the imaginary part just goes to 0. And so they are, I guess, complex numbers. They just have the sort of imaginary part going to 0. But in the C and S operations, that's where you'll actually see these complex exponentials showing up in this form in the in the tables here. But anyway, I don't want to drone on too long. As usual, the lecture notes will be linked to in the description if you want to take a closer look at this on your own. And I would also urge you to actually click on these links where I took these pictures from. I mean, they're all just the same link, but it talks a bit about these, these roots of unity and things like that. So if you want to get a little bit more understanding of that, then I would recommend checking those out. But anyway, I will see you in the next video.